Welcome to this case study about ANYmal, a quadrupedal system that we developed at ETH Zurich. In this case study, I will give you an introduction to how we built this system, how we activate the system, how we control it, and then finally come to a couple of applications of where this system is deployed today. The main motivation for building legged robotic systems is that we want to have machines that can go anywhere, that can take over the dirty and dangerous jobs from humans. These are certainly situations like this, search and rescue missions after environmental disasters. But not only that, we have job sites which are very shitty, down in the earth, in mines, 1,000 meters underground, in the sewers, on offshore sites, and even on construction sites, it's not always the nicest jobs. If you think a little bit more into the future, we are planning of creating habitats on Mars or on Moon, but we certainly don't want to send humans first to build up structures on these environments. And also here on Earth, like for example, the recent COVID situation has clearly shown that there is so many things that we still don't have solutions with machines that can do jobs in areas where we should not send humans. Now, the main reason and what all these environments have in common is that they are not built specifically for robotic systems to operate there. Instead, machines have to cope with dynamic, highly uncertain and very unstructured environment. And this is the key motivation of our research, that we want to build machines and develop their mobility and inaction capabilities to be able to operate in such environments. We have been developing legged systems at ETH Zurich for more than 10 years. What started as simple prototypes in the lab has now become a commercial product that is distributed through our spin-off ANYbotics. You see here two videos of ANYmal B and ANYmal C, the two latest generations of these quadrupedal robots that we're using in various types of environments and applications. These machines are roughly mid-dog sized, 30 to 40 kilograms heavy. They have a bunch of onboard pieces, like 3 onboard pieces that we're using for locomotion control, for navigation, and for conducting inspection tasks or observation tasks. The machine features a number of sensors like LiDAR sensors, cameras, inspection sensor to perceive the environment, to map the environment, to read out certain elements. They are made in a very robust manner that we can operate them under all kinds of different conditions. This means on one side that they have to be fall safe, and on the other side that they have to be waterproof, so they're all IP67, which means even if you put them into the water, they can still operate. The machines are designed and controlled to operate fully autonomously, so they can accurately perceive the environment and plan their navigation paths to go around that. In order to drive this system, we have been developing so-called series elastic actuator modules. These are individual joint modules that feature a motor, a gearbox, a spring between the gearbox and the motor, which decouples actuation from the output and serves as a joint torque sensor, and also motor control, electronics and sensing, all in one sealed unit, where we can just attach power and communication to it, and this individual joint unit provides very accurate joint level torque, position and velocity control, and can be used to assemble different types of robotic systems. If you're looking at the control and the autonomy of such legged robots, we typically abstract the machine. And that's not only for our machine, that's in general true for most of the quadrupedal or humanoid robots that you see today as state-of-the-art machines, as a torque-controllable, multi-articulated robotic device. Then to control, we need on the highest level a navigation and exploration planner, so somebody or a technology that tells you where to move around, where to go next, and that's actually independent of the local morphology of the system. Of course, you take into account where a system can what the mobility of the system is. A walking device might go through different environments than a driving system or a tracked system. But you're not taking care of the lowest level details, the numbers of joints that you have and how individual actuators are supposed to be moving. You're rather giving directional commands of where the system should move. Given these direction commands, you then have a planning algorithm, which in the short term time and short, close range environment of the robot, tells the robot how to move, how to place its footholds, and maybe also some reference torques or forces over a certain time horizon. So this is typically few seconds, few meters around the robot, where we are planning ahead. Then we are giving this plan to a tracking controller, which is supposed to follow that plan, to satisfy all the constraints that the machines have, to introduce maybe some reactive behavior. So all of that is typically a so-called whole body controller, which really takes into account the highest detail of model knowledge that one can have. And this generates reference commands for every single joint, and then you have low-level joint controllers that follow these commands. Now this is the command path. Then also need a sensing path. One important sensing aspect is anything related to proprioception, so sensing of internal states. We have their joint position sensors, we have ANYmals, we may have contact sensors, and all of them together are fused in a state estimator, which you can compare to like a standard wheel odometry, where you have wheels fused with IMU in order to tell how the vehicle is moving. The same thing here is that we're taking a leg odometry, combine this with the IMU in order to tell how the system is moving and where and which legs or which points are in contact with the environment. And this motion is then used both in the tracking controller as well as in the planner. This proprioceptive feedback is typically extremely fast. So we're talking here in the tracking controller about kilohertz loop rates. The same holds here for the state estimator. So this is a very fast loop, while this planner here drops to tens, maybe hundreds of hertz, and this navigation planner to a couple of hertz. There's a second feedback loop, which is including all the exteroception, which means cameras, lidars. And as we know, this takes a lot more compute effort in order to interpret this sensory information, to do localization and mapping. Hence, this feedback loop is typically slower and is used mostly in planning and in navigation. In this talk, I will primarily focus on the tracking part, which was a fundamental aspect of this class, on the planning aspect, which is one of the core research topics in the areas. So here is where the magic happens, where like many people are trying to push the boundaries to make these systems more agile, more versatile. And I will talk a little bit about the autonomy part of it, since we're talking here also about application. I will completely ignore joint level control, anything related to state estimation and proprioception, and I will also just very briefly touch upon localization and mapping through exteroception, as we need that for some of the applications. In the first part, we are focusing on the tracking aspect. I think this is a fairly well understood area. There is different frameworks out there, but they're all very similar in what they're doing. Typically, this is some sort of inverse dynamics-based control method. Many people call it whole body control or similar, where you're essentially taking knowledge of the model dynamics, you're taking knowledge about the different tasks you want to achieve with such a machine, and you're solving the problem as an optimization problem under a number of constraints. For example, how much torque you can produce in your joints, what joint limits you're having, in order to find a feasible joint level command that the robot can then finally track. For this control, we need to have a detailed model, a model of a floating base system, so a system that is not anchored to the ground, which means we have generalized coordinates which are joint level coordinates, as in any robot arm, which describe the individual joints of the legs and the joints of the arm. But we also have base coordinates which describe the position of the base and the orientation of the base with respect to an inertial frame. Now, since this is a floating base, we have an orientation which is described in SO3, which means if you look at generalized velocities, you don't take q dot, you don't do a time differentiation of the parameterization of the rotation, but instead you're looking at the linear velocity and the angular velocity of the base with respect to inertial frame and the joint level velocities. Then using these parameterizations and these generalized coordinates and generalized velocities and generalized accelerations, you can set up the full dynamics equations of motion of the system that you have here on the left. So this is mass times acceleration. Then we combine in h, we combine all the Coriolis, centrifugal, and gravitational terms. We have then on the right-hand side the actuation. And since we have a floating base which is unactuated, there is a selection matrix in the front which maps the actuated joints to the full generalized joint space. And then we have lambda, which are all the external forces acting our system, the Jacobi, which maps these external forces at the contact points of where they're acting to the generalized space. This lambda is the stacked vector of all the ground contact forces. So any point that's in ground contact produces a ground reaction force, which we have here in lambda. This is typically in 3D space. This is, and the point contact, this is a three-dimensional force in x, y, and z direction, and times the n contact number of legs that are in ground contact. The Jacobian correspondingly is also the stacked Jacobian of all the end effectors. These are all 3 by number of q's dimensional matrices. So we're only looking at the positions, and hence it's only 3-dimensional each of them. And if you're interested now in the end effector Jacobian of end effector k, this can be the hand, this can be the foot, and you want to express this in inertial frame with respect to inertial frame, you have these 3 components. You have the base offset, you have the offset part which comes in through the rotational part, and then you have the Jacobian with respect to joint level coordinates for the corresponding limb that you're looking at. So if it's an end effector of 1 foot, then this is the Jacobian that corresponds to that 1 foot which is in ground contact. Now with this at hand, we can then do whole body control. That means given a number of tasks, for example, a task that describes how the base should move in order to ensure stability, how the individual feet should be moved from the current location to a target foothold location, how we should move the end effector, but also tasks that describe how the robot should interact with the environment, define certain ground reaction forces or certain friction cones to ensure stability there. All of these tasks have to be merged together such that we figure out what is the torques that we have to apply in our generalized direction that make the system behave as we define. To do so, we're looking at these dynamics equations of motion we introduced before, and we're also looking at the ground interaction forces, so the stacked contact forces and the stacked contact Jacobians, and we're formulating a stack of quadratic programs with inequality and equality constraints that we solve in a prioritized manner. There's a small trick that we're applying here, which is slightly different to what we have learned in the previous class. What we're doing is we are splitting these dynamics equations of motion into two separate subsets. We have on one end the whole dynamics which is related to the base. So we have an upper mass matrix, which is this MB times U dot plus HB, which is equal to a 0 in here. So we have no actuation at the base, and we have the ground reaction forces which drive the base. And then we have the lower part, which is related to the joint dynamics. So in other words, what we're splitting here is an equation which is linearly depending on U dot, on tau, and on lambda into a sub-equation which is depending on all three, and another sub-equation which is only depending on two. And since the second sub-equation here has tau equal to this mj times u and h minus this js transposed lambda, we have directly determined tau as soon as we know u dot and lambda dot. So we can have this first equation as a constraint, and then the second one directly creates tau as a function of it. That means we can define now this vector of optimization as only u dot and lambda dot, and tau will directly follow from that, and then formulate all the individual optimization tasks based on these optimization variables. So we break down the locomotion problem into simpler tasks for the equations of motion, for the contact constraints, force and torque limit, and so on and so forth, and formulate that as individual equality tasks with certain weighting factor and inequality tasks with weighting factors that all of them may have different priorities. And then we solve this task hierarchically by projecting the constraints into the null space of higher priority tasks. This can look the following ways. That's the work we did a couple of years ago. We have here on the right-hand side the individual task and their priority. And as you can see, we say first, of course, equations of motion have to hold. We have to ensure that we have no motion with the legs are in ground contact. There are certain torque limits that apply. We have a friction constraint. Then we want to keep the torso X and Y position. We have a swing foot motion which should be tracked. Then we have kinematic limits. We have a main body yaw, main body height, roll and pitch, and then do at the very end the contact force optimization. So in other words, if we hit any of these limits, then we can't optimize some of the rest anymore. For example, if you're pushing now the robot into one of their limits, we can move it still the other directions, but not more. If the robot steps down this step blindly, it has an over limb extension, so it has to lower the base, so it sacrifices main body roll and pitch in order to be able to still move. If that one would not be allowed to achieve, then the higher priorities would be sacrificed, and so on and so forth. So if you have a clever arrangement of these priorities, you get a very nice adaptation to the environment, to the constraint that we're having for completely blind locomotion. We can also do this for more complex robotic systems, for example, for this quadrupedal robot that is equipped with an arm. And here, the whole thing looks the following way. First point again, equations of motion, where we formulate this optimization variable as a function of x, of the acceleration and of the force. We have force and torque limits. So we have torque limits here, we have friction constraints at the contact points. Then we ensure these friction constraints because it's a cone and we have to somehow approximate that. What we do is we make this kind of a pyramid and then formulate this linearized cone constraint in the following way. Then we ensure that the torque is within the minimal and maximum torque. We have no motion at contact point, which means the acceleration at that point and the velocity at that point must be 0. So we write this on acceleration level. Then we have a center of motion tracking task. So we have from a plan, we get a desired base motion. So we have a desired acceleration, we have a desired position and desired velocity of the base, while on the desired position and on the desired velocity we have a feedback gain to define the reference target or the target base acceleration, and we feed this in our objective for that one task and then formulate that linear constraint such that it follows the reference acceleration. Then we have a torso angular motion similar to what we did before. Now here we want to keep it to 0. Then foot motion tracking, again a predefined swing leg trajectory. We do a similar tracking task as we've seen before. Same for the end effector motion here. Then when you're interacting with something, you have a force that you want to apply at the end effector, or also if you have to lift something. So that means we can have a force at that point, which comes into our objectives as the selection matrix for that force in our complete stack of optimization variables in accelerations and forces. That one selects this reference force that we want to achieve. Then we want to have a torso adaptation. This is illustrated in this video here. So for example, if I go and grasp something, the torso should adapt. And this adaptation obviously is a function of where we want to have the reach, how the body has its configuration, and how distant this is. So the further away, the more we want to lean to that side, the further to the other side, the more the body has to roll. And we formulate this in a fashion that we say there is a nominal distance and a nominal relative orientation between the end effector and the base. And we give then this as a constraint that pulls the robot and rotates the robot correspondingly. And then the last task is just to make sure that while we are already in the friction cones that we have defined in the first task, we want to minimize the total ground reaction force, which makes sure that they are more or less equally distributed among the individual feet. And that's simply by selecting all the ground reaction forces in our optimization variable. With this all together, we can then formulate an optimization function that defines its individual torques. Now there's one additional thing. So we have then the optimization in acceleration, the optimization in ground reaction force. We bring this into the joint part of our dynamics equations of motion and calculate desired joint level torque. Now there's one addition that we're doing here, namely that this reference torque that we're actually sending to the actuators is not only this feed-forward model-based part, but that we're additionally adding again a feedback part on the position error and on the velocity error of the desired joint configuration and joint velocity, such that we have some sort of an impedance mapping around the nominal trajectory. And with this together, you get a bunch of very nice behaviors. As you can see here, this is no fancy planning at all. Everything really emerges purely from the definition of the individual tasks and of the corresponding priorities of these tasks. You see how the robot can collaborate with a human, how it can operate objects in the environment with unknown mass while being robust against disturbances, how it can adapt to something and move objects around, and how, like, as a human, you can simply interact with this machine. This concludes the tracking part, and as I said at the beginning, the tracking part in my eyes is a fairly well understood topic all around the world. Many people have developed different frameworks, but they're doing more or less the same thing. The big developments right now, they're primarily happening on the planning side, which is about creating motions, footholds, reference torques, gait patterns, and so on over certain time horizon over complex environments. And for planning, what you need to have is a model description or a model abstraction. So the most accurate model one can think of is that you take the full multi-body dynamic systems where you have, like, for every single link, you have all the kinematic and dynamic properties included. You can also simplify this. Instead of modeling every single link with a mass, you can lump all these masses and inertias into one free-floating body, which has then the mass and the inertia of that system in a nominal configuration, and then you're modeling the legs and the contact points only on a kinematic level. Or you can even further simplify that into a CMP model or a linear inverted pendulum model that is a pretty good approximation in how the center of gravity of the system is moving, but nonetheless, as you can see here, there's quite a bit of an abstraction that is happening here. And of course, the simpler the model, the easier it is to do calculations with that, so the quicker your optimizations and your planning algorithms become, but at the same time you make the largest abstraction. The second difference in the individual planning pipelines that are out there is primarily in how much integrated you look at the planning problem. So whether you consider optimization of the timing and of the foothold location and the base motion as one combined problem or as a separate problem. And still, like, most of the people and most of the work that is done now, and also what you can see in several of the state-of-the-art robots, is a separation of these elements in a clever manner, but we're more and more converging and figuring out methods and algorithms that can do all of that in one step. So why can we use the simplified templates? Here's an example of an inverted pendulum, a linear inverted pendulum, and you can see that the trajectory of this inverted pendulum fits pretty well of the center of gravity of a human while walking. So although you have a pretty complex kinematic and dynamic multi-body system, the center of gravity of that human coincides pretty much with the center of gravity of this simplified template. So in other words, if I have to predict for the human in how its center of gravity behaves as a function of the contact locations, I can simply look at that template and I get a good prediction. I don't have to look at the complete dynamic of the system. Beside walking, where we have an inverted pendulum, we can also describe running, but there we have typically a spring between the point mass, which corresponds to the center of gravity, and the contact, which is a so-called spring-loaded inverted pendulum. And as it was shown also by people doing research in biomechanics, this simplified template describes very well both the center of gravity motion of humans and animals as well as the ground reaction forces. So you see here in black, these are ground reaction forces of humans running on a treadmill in normal direction and in tangential direction, and you see in red what this simplified template predicts. So with very reduced complexity of the model, so a simple mass on a spring course in comparison to a much more complex human, the reaction that they produce to the outside world and the motion of the center of gravity look very similar. And this has been used very often in the development of feedback control laws. So for example, from this simple template, I know that if I slightly move this contact point if I have a nominal motion which stays on the same velocity, running with the constant velocity, if I make a slightly shorter step, what happens is that I'm turning gravitational energy that I have my previous apex due to the shorter step into more kinetic energy, so I'm accelerating. And if I want to decelerate, what I have to do is I have to take a longer step, so I convert my forward kinetic energy that I have more into height energy, and I'm decelerating. And even like in the very, very early works by Mark Rabert on the single leg jumping robots, what they were using was a feedback control law for the foot placement, which said there is a nominal foot placement as a function of the velocity that I want to have for running, and there is a feedback law on the difference between the target velocity and the actual velocity, which is scaled by the square root of the height. And with that, by using virtual legs for quadrupedal or bipedal system, they were able to make hopping robots and running robots stable back then, 35 years ago. So what has worked back then on these individual hoppers, the single-legged hoppers by Rabert that you see here in '86, this is the same technology, or pretty much the same technology, what is still used in many quadrupedal systems. So we implemented this here on the ANYmal robot, and you can see once you have an offset, you do a foothold planning corresponding to the error that we have at the base, make a step, and become stable again. And what you see here on the left is a separation of the planning gate pattern definition to the individual on the velocity that one typically has changed to different gates, and that's similar to what we see also in the animal kingdom. You see here a small video with the different gates that we observe in dogs. Depending on the velocity they want to move on, use that in order to trigger both the liftoff and the touchdown event, and then you can transition between two different gates by essentially having an interpolation of these phase shifters. And then additionally, what we're also doing, we're changing the timing while walking depending on the velocity errors that we're seeing. And you're seeing here ANYmal walking around with different types of gate patterns. Now here we're not optimizing the gate pattern a function of the velocity, but we're just switching them manually. The second thing here is the foothold optimization. So given a certain reference velocity, which is coming either from a high-level navigation planner or from a human commanding a joysticks, what we have to find out is what is the optimal set of footholds, like centered around the nominal center of gravity. While finding these footholds, what you have to satisfy is a couple of objectives and constraints. As an objective, as we've seen before, we are using this inverted pendulum simplification, which tells us the way how the system is moving. So we're using that as kind of a predictor, like an NPC oracle, in order to tell us where we should step in the optimal way, in the optimal case. And then we apply certain constraints to it. For example, you avoid leg overextension, self-collisions, that you're not stepping with your left foot on your right foot, and so on and so forth. And you're throwing this into an optimization function, which optimizes these foothold locations given all these individual constraints. And this optimization is actually extremely fast, so you can run this with multiple kilohertz on your system. For this foothold, nominal foothold definition, what you have given is a desired velocity. This desired velocity tells you a desired foothold location in your nominal case, and then you have external forces which give a certain error to that, so you have to compensate for this. Plus then you have these constraints which are reachability constraint, and you project this back onto that envelope, and that's essentially what this optimization here is doing. And if you do that, you're getting very robust. So you have here the robot walking with a dynamic lateral walk, and you push it and you pull it, and the robot selects a new foothold while not stepping on itself, and ensuring that you maintain stability over time. Now, given the footholds and the gait pattern, you have defined your support polygons, and you have defined a sequence of support polygons into the future. So all we need to do then is to find how the system is supposed to be moving given these support polygons. So we're optimizing for the center of gravity trajectory, where we're optimizing, which is parameterized as a sequence of quintic splines. And then what you want to achieve as your objective is that you track your high-level desired velocity that is given here, and you want to make sure that your robot tracks this velocity as smoothly as possible. And as constraints, we're again working with a simplified template description, which is in our case a CMP model that tells you in a simplified manner, given the support polygon and a center of gravity point, a center of pressure point within the support polygon, what is the relationship between the point here and the motion of the base. So we have the center of gravity location, we have the zero moment point or the center of pressure in the support polygon, and the relationship to the base acceleration. Very often people linearize this, so they say, okay, we are moving more or less horizontal with our center of gravity, so that part is becoming zero, which means it's now only depending linearly. So we have a linear differential equation in x in the x position. So we have the position and the acceleration, so differential equation in the center of gravity position. And you have to ensure that this remains within your limits. So if you have the trot, it's one line. So the center of gravity, center of pressure remains within this line. If you have three legs in simultaneous ground contact, it is a triangle. You give it certain safety boundaries to compensate for modeling errors, and then you have to make sure that your center of pressure always remains within these ground reaction or these support polygons. And with this, you're planning then the base motion. If you're doing this, you're getting a robot which is pretty robust to different types of terrains. So what we're doing here is we're walking with ANYmal over gravel piste at our testing site, the DTH. The robot is blind, so it doesn't see anything about the environment. It just adapts based on, it adapts the pose plus the foothold location based on the haptic feedback that we're getting, and we're walking relatively robustly across these types of terrain. Now what we're missing so far is perception, so everything was completely blind. In order to include perception, what we did is that we developed a mapping pipeline which does fast elevation mapping, so mapping of the local proximity of the environment in a dense fashion by fusing depth sensor information and the robot onboard state estimation. So what you see here is a dense reconstruction of the terrain around the robot, which comes in at very high frequency, and this is the information that we're using for foothold selection. We then developed a batch search algorithm which essentially looks at the terrain, figures out which parts of the terrain are the best ones to step upon depending on certain criteria, and which ones are feasible also from a kinematic point of view. If you bring these things together, you achieve pretty robust and versatile locomotion across challenging terrain. You see here ANYmal going across a cluttered environment with obstacles that are mapped, and in these obstacles the robot then selects optimal footholds in order not to step on an edge or on a very inclined surface, and to move on robustly. As you can see here, it nicely adapts the footprint depending on how the environment looks like. Now, state-of-the-art research goes now more and more into frameworks which try to do not the separation of foothold and motion and base motion optimization, but instead formulate all of that into one single optimization problem. And what has been done so far, primarily on simplified templates, is today done mostly on central dynamic models, so models which capture the big part of the dynamics, not everything exactly, and almost everything in the kinematics. And like the ultimate goal, I think we're close to achieving that in real time on the robot, is to include the full body dynamics model into these planning and control frameworks. And how the setup can look like is shown here. This is a DDP based method called sequential linear quadratic, which was developed by Farbod Fashidian, a person in my group. A framework that is used is shared open source, and there are several people around the globe are contributing to. So what we're doing is we're optimizing a control policy which has a feed-forward part and a feedback component on it. We're doing this through making forward rollouts of the known dynamics of our system. After every forward rollout, what you do is you do an LQ approximation of the dynamics and of the costs, and you also do something similar with the constraints. Then you solve a couple of Riccati equations that come out of that, and you run through this until you end up with a solution that satisfies your optimization. The key development that is happening in here is primarily on how we can handle various types of constraints, like state input equality constraints, state only equality constraints, or inequality constraint through different methods. And these are all very relevant types of constraints that we have in electrorobotic systems. There has been several innovations happening on our side. So whatever you do, even if you take here the most complex robotic system, there is still model approximation you're making. And the biggest approximations you're doing is in the actuation. What we're assuming is you are creating a policy which gives a feed-forward torque or a feed-forward torque that you're sending to your actuators, and your actuators perfectly track that. So that's the model that we're making in here. We are knowing that this is not the case. Like an actuator is never perfect. We have bandwidth limitations, we have saturation, and so on and so forth. In order to cope with that, what we did is we figured out a method where we do essentially penalize high frequency inputs. So we do we make a cost function which depends on the frequencies, and due to that we are able to ensure that the control inputs that we are generating can actually be tracked by our actuators. You can also include perception in this formulation, as you can see here in this small video where we have ANYmal walking across stepping stones. What happens in here is that we are searching on this ground, on the stepping stones, for patches where the robot can step on, and we're formulating, or we're bringing these patches which are feasible to step upon into our optimization constraints as areas which, as the name says, like you can step upon. And as you can see, the robot now jointly optimizes for how the base is supposed to be moving and where it can step by looking into the future and finding a feasible set of base motions and foothold locations. You can apply the same formulation also to the quadruped with an additional arm on top. As you can see here in these videos where the robot opens doors, and it does this door opening even in case of disturbance from outside by optimizing the way it's moving, the way it's interacting with the environment, and the way it's reacting to disturbances from the environment, all under a number of constraints of kinematic reachability, foothold, potential foothold location, and so on and so forth. Now you can even bring this one step further by not only including foothold location optimization and base motion optimization, but by additionally optimizing also for the gate timing. So you're optimizing for how the system is moving, where the system is stepping, but also at what time the system is doing a step with each individual foothold. Illustrate this with the following example. So let's assume you want to go from A to B. You have the robot starting with an initial guess, just linear interpolation. You then adapt and optimize both footholds and the motion, and you see over time how the system is getting better and better until we have found a feasible solution to go from A to B. And what you see here is in this animation is something that we are doing online on board in this optimization algorithm in a couple of tens of milliseconds. You can also do this for more complex environments where you really see also that the robot starts adapting the gate sequence, so not only doing a classical trotting gait, but really changing the footholds depending and the timing depending on the type of environment that you're facing. A completely alternative method that has gained a lot of attention very recently is that instead of doing an online onboard optimization of gait, time, foothold, and motion, we're doing this offline, and we're using reinforcement learning in order to train a neural network that giving the same commands, giving the same perception information, directly outputs joint level commands to the robot. In order to generate the data for these training methods, what we are running is a lot of simulations. What we did is we developed a simulation environment which can, on one side, do very accurate contact resolving. So instead of having a soft contact model as we see in many of the game engines, we developed a contact method which is using bisection and implements the contacts as hard contacts. In addition to that, we did a fast implementation of a multi-body dynamics solver in order to be able to generate a huge amount of data in very short time. So we can simulate a couple of thousands of robots in real time together. We then train in this environment locomotion policies, and after a couple of thousand iterations, you make a robot walk. This takes some hours on the actual system, depending on how complex you're modeling the complete robot and how much you're disturbing and randomizing the environment. Now, given this control policy, what one can do is you take it, bring it on your robot, and this is what happens. So for a long time, we had a huge problem in being able to deploy learned controllers from simulation on the real system. And the reason for that is that there is a huge reality gap. Similar to the optimization we talked about before, also in here, the simulation does not exactly capture reality. The biggest difference is that in a simulation, we are assuming that we have this multi-body dynamics description of our robot, and then what we're optimizing is a controller that takes in the state of this robot and produces joint level commands. However, this is not the truth. The truth is actually that we have in between, we have actuator units which cause a lot of delay, which have a lot of saturation effects, which have bandwidth limitations, we have imperfect tracking, we have state measurements, we have a state estimator in between, and also here we have a lot of delay. In other words, What we really have to simulate is the multi-body dynamics and all these elements which cause an offset between what you're simulating and what is reality. What we are doing is that we went to the real system, we took data, and with this data we approximated all these unknown dynamics that we have, in particular in the actuators, through neural networks, such that we combine two things. We combine something that is easy to model but difficult to learn, the multi-body dynamics, with something that is very difficult to model using first principles but relatively easy to learn from data. We then set up a reinforcement learning pipeline which does a stochastic variation of certain properties of your model that you're simulating. We bring in variance in the mass, in the link length, and so on and so forth. We combine this with learned actuator networks in a reinforcement learning loop, train a policy. For those who want to see the details, here is the complete architecture, how it looks like. As you can see, we have relatively simple networks. So for example, the actuator network here is only a 3-layer network where we take in velocity measurements and position measurements, a history of them that we can also capture time dependency, but there is no memory in the network at all. And by that, we are predicting from this history of position errors and velocities the torques. We then have this as complete simulator, and we train a control policy which has only 2 hidden layers, a pure feed-forward policy, where we take in, and again this is important since we have no memory in the control policy, we take in a history of measurement data, of velocity, of positions, of the complete QNUs that you can measure on the robot, as well as of the body pose, body twist, which is coming from the state estimator, and use that for our control policy. With this together, things finally started to work. We could have this was 1 year ago where we released this to public, showing for the first time how reinforcement learning can make a robot, a complex robot, walk extremely robustly, robust against external disturbances, with very high speed and extremely high efficiencies, are much better than what we achieved previously with optimization-based technologies. The nice thing is that you can not only optimize for locomotion, but you can actually compose complex behaviors out of multiple individual behaviors. Here we trained for self-rightening, for standing up, and for locomoting, and we then created a behavior selection algorithm, which, depending on which state the robot is, selects the right behavior. That's also done through reinforcement learning. If you bring that together, we achieve this. You see, you can throw over a robot, it falls to the ground, but it immediately figures out the way in order to stand up again and continue to operate. In fact, you can put the robot in almost arbitrary configurations on the ground, and it will find a way to recover from that and continue to operate. This on one side makes our robots extremely robust. I see here a PhD student playing around with the robot. It also requires us to reconsider a little bit what we consider as stable for these robots. So if a robot falls down and stands up again, is it dynamically stable or not? But it also shows a little bit in where the mobility of these machines will go in the short term or mid-term future. In fact, if you look at the simulation and the real-world data, both initialized with the same initial conditions and the same control policy, you see that there's a huge, a high level of agreement between the simulator and the real world, and that is the key reason why we're actually able to train everything in simulation, then put it onto the real system. Now, if you go back to my very first slide where I showed you the different types of environment where we would like to deploy these robots, and I have a couple of illustrations here of the animal being there, we see that this is distinctly different to what we have observed in all these environments in the lab. There's large variations in the terrain, and the thing is that depending on the type of terrain, it's extremely hard to model these terrains, and it's also very hard to perceive that and to classify that. And even if we could model this terrain, you would not even know of what you would do with the corresponding sensor information. So we had to come up with a method that allows us to train the robot independent of the terrain it will face, and then extrapolate that such that it can cope with what it encountered during the deployment. And what we're doing is we are taking kind of the similar structure that you've seen before. So we have a MLP that we are optimizing, optimizing in order to, as a locomotion policy, we're using a standard RL algorithm. In that case was TRPO, policy gradient algorithm. And what we are doing here especially is that we say, well, in the simulator, we have a lot of information about the environment. We know exactly what kind of contact state we have, what kind of contact forces we apply, what is the terrain profile around the robot, what are the friction coefficients, what kind of disturbance that I'm having. And what we're doing now is we are creating a MLP encoder which takes all these informations, compacts that into a latent information that is used by the controller in order to react appropriately. Now, as we know, this information is not available on the real system. So what we want then is, in a student policy training, is that we clone this MLP. So we take the same MLP here, copy it here, but we want to recover this latent information that is given as an input to the MLP through a TCN network, which takes a history of data and estimates the same latent information. And we do imitation learning to achieve the same with the student. Additionally to that, we make an adaptive curriculum. So the better the robot gets, the harder we make it, the harder we make the environment, the more disturbance we apply to the robot. And as you can see in these videos, there is a certain set of different discrete types of environment that you're training the robot for. And the big hope was that this really generalizes well to the environment, to unknown environments. And actually it does. As you can see in the video here, the robot is now able to walk across all kinds of different challenging grounds it hasn't seen before, and it hasn't seen in simulation, but what we trained in simulation extrapolates very well to these types of environments. And that was actually a game changer. It allowed us to have our robot walk in all kinds of challenging natural environments with sliding and slipping grounds, where you have, like in this riverbed, rubbles that are moving around, surfaces that are extremely slippery, and the robot just robustly goes through that. There's many things that are very nice to investigate in more detail. For example, as you can see here, the robot walks into a obstacle, then it triggers a reflex and starts stepping onto the obstacle. Remember, all of that happens while the robot is blind, and we never handcrafted an obstacle or a reflex behavior from a high-level human intuition. In fact, what is happening in here is that if you look at what this TCN network assumes about the environment, is that in the first part, while moving, while not colliding at all, we assume that there is certain uncertainty in front of the robot, but not too big. Then you're walking and you're colliding with something. As soon as you're colliding, you know that the terrain is not flat anymore, but it must be higher up, and also the uncertainty is getting bigger there. Once you're stepping on it again, you get the correction factor, so you can decrease your uncertainty again and you can continue to walk. And the nice thing is, if you look at the sensitivity of how much your behavior depends on sensor signals that came into the network at a certain time, you see that the step when you hit it first, still has an influence on this higher step, which was triggered then as a reflex certain time afterwards to step on the object. The nice thing is you can also deploy the robot now with certain unknown payload, and it will still work. So this unknown payload is a disturbance. The robot estimates this disturbance and just compensates with the behavior. So it was never told that there is additional mass on it, but through the randomization, through these disturbances that we're giving in simulation, it is able to compensate or to cope with that and to locomote. It's also nice how it reacts to slippery surfaces. So you see here the robot walking across a whiteboard which is wet, so we have a friction coefficient that is extremely low. And if you look at what this network is predicting, is that while walking on the normal ground, you have an estimation of the friction coefficient which is very high. Now, the first time you're stepping on the whiteboard, you see that you realize that the robot slips. So immediately, in very short time, we're decreasing the estimated friction coefficient to a very low number. And then we're walking while being on this whiteboard, assuming that there is a relatively low friction coefficient. So we are distributing the ground reaction forces in a different way. We are adapting certain gate parameters. And then once we're stepping off this whiteboard, this happens here. So we have again ground underneath the feet, which is not slippery. You see that how slowly the robot starts being confident again that there is high friction on the ground, cranks up the estimated friction coefficient, and walks again in a fashion that is optimal for higher friction. Now we have everything at hand that allows us to deploy our robot in a real-world scenario. The only thing that is missing is that we need to have environment perception. For this, the robot is equipped with a variety of sensors. We have a Velodyne sensor to create a 3D point cloud of the environment. There is active stereo sensors, Intel real sensors all around the robot, so 4 of them to create an elevation map of the environment. There's wide-angle cameras in the front and in the back, and we have RTK GPS for outdoor operations. In addition, on top, we have a pan tilt head with zoom camera, thermal cameras, light for inspection tasks. When the robot moves around, we use the Velodyne sensor in order to map the environment. We're doing this through either ICP or LOAM. These are 2 of the most standard frameworks that are out there in order to do 3D mapping and localization using LiDAR. So in short, what this is doing is we're taking a scan, we're moving by a certain distance, we're taking another scan, and then we're aligning these 2 scans in a so-called scan matching, and by that we are mapping the environment and we are localizing ourselves within this environment. You see here one of the examples where we're doing some of our field trials. This is the search and rescue training site in Wangen-an-der-Aare, where we had the robot walking through the complete site several times, creating a full 3D map of that thing. So that's about the quality that you achieve with that. Typically with automotive grade LiDAR, we're talking here about few centimeters accuracy that we have in these 3D maps. In addition to that, as you have seen already earlier, we typically do not only make a 3D map with these point clouds, but we're also mapping through these active stereo cameras around the robot the local terrain and use that then for foothold planning. Now, geometric information about the environment is not everything. Typically, you want to know more than just the geometry. For this, what we are doing also is we are fusing multimodal sensor information to do an estimation of the terrain quality. So assume you're walking through certain environments where you see the environment and then you were stepping on the environment afterwards. So what you have is visual feedback of the environment, and you have a like a reaction feedback of the environment from a force torque sensor, from your IMUs. You know whether you were slipping at a certain point, you know whether you had shocks at a certain point, oscillations, vibrations, whatever. So what you can do is you can combine these two sensor signals, you can label your data, and then use that data in order to predict the terrain quality in the environment that is in front of you. And it turns actually out that it is pretty straightforward to make a very nice application. You see here the robot walking. It sees a street in front of it. Here two streets, one going to the left, one going to the right. And you see here in the middle how the ground reaction score is estimated. There's very clear colored patches for terrain that is good on the street. Here's a sand pit on the side, which is bad to move on. And by that, they can use this information in order to autonomously navigate around the environment. Here we gave a goal point up there, and the robot selects the street to walk along. It doesn't go into the sand pit. You have here grass on the side, and only goes into the grass once it's necessary in order to achieve this goal location. Together we have now the possibility of sending ANYmal into all kinds of real-world applications. Here's a couple of them that we are investigating actively. There is search and rescue, sewer and mine inspection, we have underground exploration, some work in forest, and a lot of industrial inspection, in particularly through the spin-off company ANYmal. I will show you some highlights of some of the deployments we had in the last couple of years, and hope that you get kind of a glimpse of what is possible or potentially possible with these machines in the future. In search and rescue, we are working together with a lot of colleagues all around Switzerland in the NCCR Robotics, which is a big initiative in robotics across Switzerland, towards having robotic systems that can be deployed for search and rescue missions. That means we have ANYmal being deployed, for example, in a collapsed building, while an operator stands outside, teleoperates the robot, gets the sensory feedback from the robot about the 3D environment, about thermal images, about RGB images, and by that can actively search, for example, for victims in such environments. Then we're working in a European project on sewer and mine inspection. For this, the robot is deployed here in the sewers of the city of Zurich. It is equipped with new feet where we have additional sensors incorporated that are used in order to measure the level of concrete deterioration and the amount of sediments that is on the ground through haptic inspection. So we're scratching with the foot on the ground, we're measuring oscillations, ground reaction forces profiles, and by that classify the environment. We're also doing autonomous exploration of underground areas. This is a DARPA competition, the DARPA Sub-T Challenge, where we are collaborating with an international team from US and Europe. You see here ANYmal being deployed in Zatzop in a nuclear power plant where it's supposed to automatically explore a large-scale area. You see a couple of video streams here grouped together. On the bottom left we have the elevation map, so the mapping of the proximity of the environment that is used, the proximity of the robot that is used for foothold planning. You see on the top left the forward image stream, which is used in order to find objects, find artifacts in that environment. Top right shows you the ongoing 3D map from a top-down view that is assembled from the point clouds. And on the bottom right you see the volumetric reconstruction. Now what you're doing is that in this volumetric reconstruction we're searching for directions where we have the optimal information gain. That's the path that you see that is planned in front of the robot. We're checking for traversability of this path and then have the robot navigating from waypoint to waypoint without human interaction, finding artifacts in this environment and like bringing back a complete map plus the location of these artifacts. This is a classical 3D map that is created in here. This was the entrance. You saw the robot first going through these tunnels all the way straight and into the reactor building, all the way around until this dead end and then coming back. This was a distance of several hundreds of meters. This circle in the middle, for your reference, this is the reactor building, so the diameter of the cooling tower. And then the last type of application that we are primarily exploiting for commercial use is industrial inspection. Here you see ANYmal working on a collector platform in the North Sea. This was a showcase that we did together with Tenet. The robot is moving around in this environment doing inspection tasks. It is equipped with this instrumented sensor head with cameras, thermal cameras, and acoustic sensors. It then maps the environment, it finds navigation path through this environment, and does follow a couple of inspection points. So here the first point is a thermal inspection, then we're checking the location of a fire extinguisher. We are reading out certain displays, and we're not only looking at them, but really taking images, interpreting the images, and delivering exact feedback about, for example, what kind of pressure is there. We're searching for leaks and so on. Similar to this inspection that we did offshore, we do also inspection of construction site to observe the state of the construction, to find whether there is any obstacles on the ground for example, for safety measures. Here, this is an example that we did with Marazzi Losinger in Zurich, where we have the robot navigating on the construction side of a hospital. You see again how the robot maps the environment, localizes itself within this environment, and does a couple of visual inspections, for example, whether these elements have the right temperature, if there's anything broken or not. It can again walk through all kinds of different terrains and environment, doesn't matter whether it's wet or not, if there's obstacles on the way. And this is really something that enables a lot of new applications in the future. With this, I want to close here. I hope you enjoyed the overview about the example of ANYmal, of research that we're doing at the lab, and a little bit of what we're doing at ANYbotics towards commercial application with that. If you're interested in more information, go to our homepages. If you search for Electrobotics on YouTube, Bitbucket, GitHub, on Twitter, you find a lot of additional information. If you're interested in joining our team, I think it's we have an amazing team. It's a lot of fun, and you're more than welcome to either do a thesis or even maybe start a PhD with us. Thank you very much.